Okay, first new thing for today. Last night I'd asked you to look into direct current and alternating current. Direct current is called DC, alternating current is called AC. The unphysics people among us often will say DC current or AC current. But really, if you say that, you're stuttering because you're saying direct current or alternating current. So it's just AC, DC. Hey, that'd be a good name for a band. Okay, so direct current is really what we've talked about in physics and what you've seen in science all along. Direct current means the current, my notes are really bad here because they're photocopier, but it means it flows in one direction, right? So a current leaves a power supply, drawing it as I'm talking, leaves a power supply, flows through the circuit, comes back to the power supply, flowing in one direction. So any of the circuits we've looked at would be direct current, okay? And it's what Thomas Edison was a proponent of. But really what we use most in our life is alternating current, okay? So it's current that changes its direction many times in a second, okay? It reverses directions many times per second. And it's usually sinusoidal. And I can give you a copy of these notes when I see you again. I just want to talk about how we make this alternating current. We make it by something that's called an electric generator. And I'm sure you've all heard of generators, especially when the power goes out. It's really a very simple principle. You have a big magnet, or two magnets, okay? And you have this coil in between them. And what we're going to do is we're going to turn the coil. And when we turn the coil, if you just think of this one side, okay, so this one side of the wire, as we turn the coil, and I have it turning down, going down into the field, it now becomes a wire that's moving in a magnetic field. And a wire moving in a magnetic field is going to get an induced EMF and have a current flowing in it. And if I have to use conventional current because I'm using my left hand to hold the iPad. So if we think conventional current, the wire on this side is going down. My fingers have to go north to south. I can't show you that. And so the induced conventional current would flow this way. Okay, so this is going to go down into the page. And then it's going to, but as it goes down into the page, the field down below the magnets is going to get weaker. And so the current is going to get weaker because remember, EMF is equal to BLV. So if the field is weaker down there, then the induced EMF is weaker. And then, of course, I would also be smaller because it's going to be your EMF divided by R. Okay, so it's going to be at maximum EMF when it's directly in the middle of the magnets. But then as we swing it down, and it's going to go down and around and come back up on this side. So now this one is going to be over here, and it's going to be on its way up. Well, when it's on its way up, now the current, I lost my pen, now the current will be flowing in the other direction. But it's still in this side of the wire because this side of the wire will be over here. So can you see that? Like, so we start at the top, and as it goes down, the field's getting stronger and stronger and stronger. So the current will be flowing towards us, like towards the bottom of the screen here. And as it goes, hits the directly between the poles, it'll be at its maximum. And then as it keeps going down to the bottom, it'll get weaker again, but still flowing in the same direction. When it hits the bottom, it'll be 0, and now it'll start to come up the other side. Well, now it's not going down anymore, it's coming up. So the direction of the current in this branch of the wire will have to flip, and it'll now be flowing the other way. So as I spin this, what happens to the voltage and the current is this. Right? It flows one way. As it goes down, it gets bigger. So right here would be when it's in, like, directly between the two poles. As it keeps going down, it gets smaller again. It stops. And now as it comes up the other side, it changes direction and gets bigger, when it's back between the poles, it's at its maximum in the opposite direction. It's going to be all the way up here out of the page. It's going to be 0 again. And now it's going to turn and go back down the other side. And it's going to have get bigger again, but in the opposite direction. So this is why we say it's sinusoidal. So as I spin it, then I can increase the frequency of the spin. And so the bigger the frequency, like the closer together these waves are. If I want to get more current or more voltage, what I would do would be add more coils, right? The more coils, then the more current that would be induced. Okay, so this is all a generator is. This might be a better picture than the one I have there, but it's the same idea. There's a good picture on page 519 too, if you have your book home. So as you turn the handle, the coils cut the field, the current flows. As you keep turning, the current reverses again and again. The more coils, the more current. The faster you turn it, the more current. The stronger the field, the more current. So this is how we can create current from mechanical energy. Mechanical, I'm doing physical, using physical energy, doing work, and I'm creating electrical energy. So a generator, invented by Michael Faraday, converts mechanical energy to electrical energy. Okay? It's the opposite of a motor. A motor takes electrical energy and converts it into mechanical. Okay? So if you think of any motor you have, you plug it in, you use electrical energy, and it converts to mechanical. Okay? So that's an electric generator, and it's how we get AC as opposed to DC. Okay? Alternating current opposed to direct current. Now, if you were to look at countries, you would discover that different countries use different frequencies of AC current, AC. And they also use different voltages. So one of the things I would like you to do before you come back is just do a little Google and find out, like, what's our voltage and what's our frequency here in North America, Canada and the US. What is it in Europe? What is it in Asia? And why are they different? See if you can come up with how come we don't all use the same. Okay? So that's AC, DC, and generators. The other new piece, I was going to go to transformers, but I think I'll wait until after we have a conversation about why they're different. So the other new piece I want to do with you is connecting electric fields and magnetic fields. It kind of, it jumps a little bit, but I just thought it would be easier than, and leave the tougher stuff to when we're together. So connecting electric fields and magnetic fields. So if you remember, back before the last test, we had like a magnetic field, and I might run out of time here, but I'll try not to. We had a magnetic field like this going into the page, and then we took a little charged particle and we sent it into it. And if this charged particle was positive, then it would experience a force that would cause it to curve upward like this, right? And so it would end up with a circular path that was counterclockwise. Well, somewhere around 1900, there were two guys, J.J. Thompson, who you might know from the models of the atom, and Milken, who were working with small charges. Too bad I can't spell Milken, M-I-L-K, M-I-L-L-I-K. Oops, there's two L's there, A-N. They were working with charges and were able to isolate a charge. And so what they did was they said, what if we don't want this guy to curve upward? If I don't want this guy to curve upward, something I could do is I could put metal plates on either side and create a field, an electric field. And that electric field could put a force on this charge as it goes to curve up, causing it to go straight. So I want the electric force, and remember E is equal to F over Q. So I could set a field up big enough that I would have an F that would balance out the F that is equal to QVB sine theta. So if these two F's are equal, then E will be equal to QVB sine theta over Q, and I'm going to run out of time. The Q's cancel. And the B and the V are parallel, and we get E is equal to VB.